Hi, my name is Chris Michael, and I'll be presenting a study on interactive machine learning and the potential of cognitive feedback. I work at the U.S. Naval Research Laboratory's Center for Geospatial Sciences, along with my co-authors Dina Ackland, who is an experimental psychologist, and J.L. Schuerman, who is a computer scientist focused on cognitive models. For those unfamiliar, the Center for Geospatial Sciences is located at Stennis Space Center, Mississippi, just along the border with Southeast Louisiana. I'll start by saying that this study does not present empirical results or novel techniques, but we feel that it's a necessary contribution nonetheless. The study was inspired by the many failures we've seen within the defense sector when state-of-the-art machine learning implementations are painstakingly transitioned only to have them thrown out by analysts and other customers in the end. So this is about stepping back, identifying the reasons why this keeps happening, and presenting a general objective solution to the problem. The purpose of this study is to highlight a major gap in defense machine learning and to present a convincing argument that interactive machine learning, or IML, can fill that gap. Furthermore, we'll discuss the state of the art in IML by delving into an example application and identifying the potential roadblocks ahead. As part of this, I will explain why we feel cognitive feedback is an imperative missing piece to an effective IML implementation. Finally, we offer a taxonomy that categorizes the possible ways cognitive feedback may be used to inform IML. The most common reasons why state-of-the-art machine learning models fail typically deal with the particular nuances of defense applications, from the data to the model itself to the user. Looking at the data first, of course we know that most modern deep models that boast great results need a lot of training data. And this data has to be curated. Typically, there is not a trivial amount of work involved with taking historic data and turning it into a good training set. Furthermore, if an adequate training set is not available, who is going to put the labor in to create the data set? How do they know how much labeled data is enough labeled data? Correctly verifying the model may also take weeks to turn around. In active learning literature, there are two studied phenomena that address problems when learning is performed on data streams, such as those used in so many defense applications. Concept drift addresses the fact that properties of underlying data may change over time. Examples of concept drift include changes in region of interest, where an application's training data may overfit to a unique region, or new types of modalities of data, which could be as simple as having a new sensor calibration or as complex as having a new sensor type altogether. Concept evolution has more to do with how the features we want to classify change over time. For defense applications, this could be a change in mission requirements. For example, the definition of what constitutes hazardous terrain may change as the mission evolves. Another example of concept evolution is when new intelligence is required by the mission, which may happen abruptly. Concept drift and concept evolution are very important concepts to consider for defense applications, yet they're often neglected by the machine learning products we build for defense. Finally, and most importantly, is the issue involving the human in the loop. Deep models typically present all or nothing solutions to the analyst. Allow me to use region digitization as an example, since that's my team's main area of expertise. The image shown on this slide is a lake that has been digitized by a machine learning implementation that boasts 99% accuracy for performing segmentation of water on color imagery. Though the pixel accuracy is near this value on this particular image, some artifacts in certain areas of the image cause the segmentation to perform inadequately. This is mainly due to the fact that this image was captured when the lake was dried out. Though the classifier's accuracy is still quite high, about 5% of the contour is not up to par, as can be seen in the east and northeast parts of the lake. In our experience, an analyst will not typically work with such a product even though most of the work has been done for them. There are several known reasons and probably many unknown reasons for this behavior, but intuitively we can say that all or nothing automatic solutions must work near perfectly to be adopted for use. An IML application has great potential for overcoming these problems, and I hope to do a decent job of presenting why we think this is true. In order to explain the IML paradigm, it's important to review the critical data flow of conventional machine learning, which we refer to as automatic machine learning, or AML. For the vast majority of AML implementations, information flows in one direction. The training data is used to update the model, which is used for classification, which is presented to the user. I do not present this figure as a sweeping generalization. However, for the most part, this is the critical path of most AML applications that are transitioned into defense. The models are providing decisions to the analyst. The analyst either chooses to use it, may be able to adjust it slightly, or just will discard it with no active feedback to the model. IML is fundamentally different in that it is built around the analyst. IML assumes that the model will be incorrect at times, and that there is a human in the loop to provide feedback about those mistakes. But presenting guesses to the user is not a trivial matter. Depending on the application, you can expect IML implementations to have highly specialized software interfaces. These interfaces are typically built to minimize the cognitive load of verification and correction, and if necessary, to constrain the problem for optimal human-machine teaming. This integrates human-computer interface research that isn't typically leveraged with AML implementations. Having this tightly coupled loop between the human and the machine enables solving the all-or-nothing approach of AML implementations because the interface may be designed to iteratively solve the problem. Additionally, this verification loop allows for IML implementations to possibly work with no initial labeled data, since the user is implicitly labeling the data during this process. Because IML necessitates this type loop of refinement based on the user's verifications and corrections, it's very important that the classifier model is able to be updated with newly labeled data very quickly and apply that data thereafter. Therefore, IML implementations will typically use online machine learning implementations such as k-nearest neighbors and stochastic gradient descent, just to name a couple. The specific definition of online implementation leaves a lot of room for interpretation, but for the purposes of this presentation, online learning simply means a classifier can train incrementally on relatively small batches of data with a quick turnaround time. In some circumstances, the IML implementation has a lot of elbow room in choosing what guesses to send the analyst for verification. In most cases, the goal is to make the implementation as accurate as possible with a minimal amount of guesses. Active learning can be used to achieve this goal by asking the most relevant questions from a statistical perspective. In other words, asking about data that looks most unlike currently labeled data. Active learning may also be used to balance exploration versus exploitation for certain problems when doing so may be beneficial. Finally, just because an analyst has to sleep, it doesn't mean the IML implementation has to. Feature and hyperparameter optimization may be performed during downtime so that when a user comes back to work, they have an optimal machine model to work with given the data that they've previously labeled. This is analogous to AML optimization. However, online machine learning implementations can greatly benefit from these optimization steps. I will now take some time to present an example application of IML in detail. The one my group is most familiar with is the Geospatial Region Annotation Interface Toolkit, or GREAT for short. The GREAT work has been published previously, but I think it's important to give a detailed overview of it within the context of IML. In the DMAIDA paper, we discussed two other applications, language translation by Gonzalez Rubio and Casacuberta, and a biological behavior video annotator called Java. Unfortunately, I won't be able to discuss these in detail due to time constraints. We ask that you give those papers a read if you're interested. For those who may be unfamiliar, geographic region digitization involves drawing a piecewise linear polygon around some region of interest found in remote sensing imagery. This is usually done within a GIS, and the resulting vector will be stored in a database with some class label, such as wetlands in the case shown here. An analyst will use the mouse to click and create vertices along the perimeter of the region of interest. They can then go back to click and drag mistakenly placed vertices to correct the location. This is quite an arduous task to do on a large scale, as you can imagine. There are literally hundreds of automatic approaches in the literature which attempt to create such digitization automatically. These techniques range from using active contour models to more complex machine learning approaches. However, analysts do not typically adopt these approaches for several reasons. The most common reason is the one already shown on the introductory slide. These techniques tend to be all or nothing, and if the result is not perfect, it's often frustrating for the analyst to correct the mistakes. The more interactive geometric techniques such as active contour models have frustrating interfaces or possess perplexing parameter spaces. We'll now consider GREAT, which is an IML implementation for such region digitization. In this case, the key to a good human-machine interface is to maintain the complex balance between problem constraining and usability. Constraining the problem allows for the machine to converge on the task as effectively as possible. However, constraining the problem too much causes the interface to become unusable to the user. On the other hand, if the problem definition is left wide open, it becomes difficult for the machine to adequately calculate the user's intention. This is the delicate balance that makes human-computer interface research critical to the success of IML. A good analogy of constraining the problem to maximize the convergence of automation is autonomous vehicles. Those on rails have been automated for decades, while the less constrained problem of a car on the open road is still a challenge. When considering the human-machine interface, it is important to consider effective ways to constrain the problem. GREAT constrains the problem of region digitization by defining a linear search space for each vertex of the contour. Assume that some contour is instantiated in this image where wetlands are shown. Upon instantiation, there will be some search space, which is shown in the image as the broken yellow line. The red line is the current unrefined contour. Since there is only one vertex, the contour is shown as a line perpendicular to the search space. The user will click and drag this vertex and move it to the region that they'd like to annotate, which in this case is the boundary between the wetlands region and the water. The machine can then examine all the pixels of that search space and label them based on which side of the contour they lie on. The contour will then be refined with the machine implementation choosing insertion points for new vertices along the contour. New search spaces will be created that intersect these insertion points, and the machine will attempt to place each new vertex within its search space. The second image shows one correctly placed vertex, the one on the bottom right, and an incorrectly placed vertex towards the top left. The user simply clicks and drags this vertex to the correct location where the wetlands region begins. Once again, the machine can learn about the incorrect placement through this correction. This process is repeated until the wetlands region is completely contoured. But there are very important considerations that must be made regarding this process. How many vertices should the machine insert for one iteration of refinement? Too many may lead to confusion. Too few, and the machine is working behind the pace of a human. Where is the best location for vertex insertion? If the machine determines where vertices are being inserted, then it's important that the machine choose a location that will yield the most information once that vertex is confirmed or corrected by the user. The answers to these questions lie in modeling uncertainty and correctly implementing active learning. GREAT requires the machine learning implementation to be one that provides some calculation of uncertainty along with its predictions. For machine placement, the pixels of the search space are classified and a specialized algorithm is used to find the correct placement given these classifications. The image shown here at the bottom left gives an example, where more confident classifications of pixels appear a more opaque blue for pixels classified as shore, or more opaque red for those classified as water. Because each of these classifications have some value of uncertainty associated with them, the machine can calculate the uncertainty for the entire signal, and thus each insertion point along the contour has an associated measurement of uncertainty. Through experimentation, we were able to find that the calculated uncertainty of an insertion point matches the probability of correct machine placement if a vertex was to be inserted at that point. Therefore, it is possible to calculate some expected value of misplaced vertices. We use this model to scale the refinement. As the machine implementation becomes more familiar with the task at hand in the current image, it will be more aggressive with the number of insertions it performs at each iteration. This is shown in the video of this slide. Shown here is the machine placement results set from the main GREAT publication. Results were collected over 4 sets of images, 4 images per set. Each set was annotated from cold start, meaning no prior training data was used, and each digitized image is used as a training set for subsequent images. The rows of this multiplot represent different data sets, while the columns represent the images of those data sets. The x-axis for each plot denotes the iteration of refinement. The blue line series shows the number of new vertices inserted by the machine model, while the green line series shows the number of vertices that were incorrectly placed and corrected by the user. The orange line series is the expected number of incorrect vertices yielded by the uncertainty model, which is a number that should always hover around 2, an intuitive choice we made as a reasonable cognitive load. The uncertainty model performs best when the green line hangs around the orange line. For the 2 highlighted datasets, the uncertainty model performs very well for the most part. Though these datasets exhibited quite a few variations across their images, such as algal blooms and water reflection, the uncertainty model performed very well. However, the uncertainty model for the first dataset was underconfident. This meant that the number of expected corrections were predominantly greater than the number of total corrections. The machine implementation would most likely be able to insert vertices more aggressively in this case. But the most interesting result is that of the third dataset's last image. On this particular day, the lake was more dried out than usual. The machine model had overfit to the spatial location of the shoreline, and thus many mistakes were made by the model. This is an example of concept drift. The main features that designated the shoreline have shifted more to color than the geolocation once the lake dried. The uncertainty model's performance was greatly affected by this overfitting, and thus the number of incorrect vertices per iteration almost doubled above the threshold we set. This particular example is extremely important when thinking about the challenges of IML implementations, human-machine teams, and streaming data in general. Because the IML paradigm is an online paradigm, it will always be subject to such scenarios. How may the machine overcome this type of bad correlation if it has entered a new modality of the data stream? This particular example inspired us to explore the answer to this question. Ultimately, we feel that there is only one way to resolve problems with model overconfidence and underconfidence in an IML system. More input is needed from the user of the application, but not just corrections for the machine guesses. The user must provide cognitive feedback relating to the problem at hand. Take, for instance, these 3 figures above that represent an analyst digitizing some region using GREAT. The image to the left shows an underconfident model. In this case, the analyst is not being stimulated by the machine's attempts at placing vertices. The analyst could probably do much better digitizing the region from scratch. The image to the far right shows an overconfident model. In this case, the machine has attempted to do too much, and the analyst is overwhelmed by the amount of work that needs to be done. The goal is shown in the middle picture, where the machine is working at the pace of the particular user. The fact is that to truly know this pace, the machine implementation's interface and uncertainty model must be informed of the user's cognitive load given the task at hand. This is not an undiscovered fact in IML literature. In fact, all studies we mention in our paper mention cognitive load and discuss minimizing it. However, the cognitive load is usually assumed as some arbitrary constant set by the authors. We haven't come across any studies that feed cognitive load back into the uncertainty model for IML. This brings us to our study's offering, a taxonomy for cognitive feedback into IML systems. All cognitive feedback may be placed into these 3 categories. Self-reporting, which is simply a survey of the analyst that can happen in situ or through evaluation. Implicit cognitive feedback, which is where human factors research is conducted to collect and evaluate biofeedback when using an IML application. And finally, modeled cognitive feedback, where the cognitive process of an application is simulated by a computer program. I'll now quickly run through examples of each of these methods of cognitive feedback. The simplest method is self-reporting. Implementing self-reporting can be done online during use of IML applications. The example I've shown here simply adds buttons to the interface that a user may push if they feel the cognitive load is too little or too much. Though providing these buttons is trivial, incorporating this into the uncertainty model of an IML implementation is not. We feel after our literature review for this paper that there really wasn't any insightful research on how this straightforward human-provided feedback could inform the active learning and uncertainty model of the classifier. Our group is currently looking at techniques by which this can be done. While self-reported responses can be helpful, it can also come with issues that limit its usefulness in modeling applications. For one, it puts the burden on the user to provide explicit cognitive feedback for the current task at hand, but this may not always be so straightforward. Conversely, implicit cognitive feedback allows for insight into a user's cognitive state without biases or task interference. One way to capture implicit cognitive load feedback is to gather pupillometry or eye tracking data in closed experiments of the application. The data may then be used to model and profile cognitive load for the task at hand, and this feedback could be used to improve the IML model. Applying implicit cognitive feedback into machine learning models is becoming a hot topic in recent literature. There are several studies mentioned in our paper where implicit cognitive feedback, such as eye tracking gaze information, is used as a feature in order to improve results for paradigms such as reinforcement learning for playing video games. Cognitive models and cognitive architectures have long been used to simulate human behavior. Cognitive models seek to model specific processes, such as using instant-based learning to model memory processes, or drift diffusion to model the speed versus accuracy trade-off seen in a variety of decision-making tasks. Cognitive architectures such as ACT-R and SOAR seek to model cognitive processes in the context of a mind as a whole. ACT-R in particular provides tools for modeling perception, memory processes, and motor processes, and is capable of simulating average performance in a task, including accuracies and timings. By comparing the model to human behavior, we can validate the models and then use them to inform the design of interfaces and systems. It is also possible to use cognitive models online to analyze cognitive load for unique situations in flight. I hope that I've done a decent job of convincing you that IML can be a good fit for many defense problems, and that for good IML implementations, we need good cognitive feedback research. We're currently working on several research projects that incorporate cognitive feedback in each of the categories I presented in our taxonomy. Here's some contact information along with the current sponsors of our work. Thank you for taking the time to listen to our presentation.